Okay, so the live stream's running. I know of at least one student who's not here because they had to isolate. Maybe more. The hope is that the live stream will get them almost the same experience as being here in the crowded room. So we'll get started in a second. Let's have a quick look on Slido. It's best practice for you to always sign in when you come in, so that we don't lose much time when I later surprise you with the next question. So this one's not a very interesting one, so that won't count, but I saw this went up by at least 20 people from this morning. Before we start, any questions about organization or any questions about CompassWire so far? There was one announcement I wanted to make about the tutorials. You might have seen Ben just posted earlier today a poll on CompassWire where he asks you what your preference is, how to organize the tutorials. So, well, his plan is described there in more detail. The idea was to have one session only online, so that it's so that he can make sure that that works properly, and he would do it from home. And the other two sessions on campus, and you're not necessarily bound to the group that you're assigned to, but of course you might have other things timetabled, so it might not work. Please have a look at this on CompassWire and check out the detailed dates that he put there. This will only start next week, so no tutorials today or tomorrow. We start next week. We have a little sheet with exercise problems prepared for you that I didn't get around to put on the website today, but can do it after class. Yeah, I think that's pretty much it for now. We'll talk about the video presentation in a week or so again. Any questions organization-wise? If that's not the case, then let's jump into today's topic. We're still in Unit 0. So it's still a bit of preparations before we really get into algorithms. So welcome back to COMP526. Still Unit 0, but now actual content, even though not algorithms per se, but some proof techniques that we will use or at least rely on implicitly in the module. Some of you will have seen a good deal of this, but some others won't. And so it's kind of a quick run through what I think could be useful without going into very much detail. Some of the things will be practiced a bit more in the tutorials, so you will have a chance to practice that a bit more. I tried to put some learning outcomes for each and every unit on the slides. And so here, the idea is to know certain standard strategies. This will become clear what I mean by proof strategies. It's just a way to get started. It doesn't really help you to solve any particular problem, but it's a scaffold or a template to start from. And we'll look at the typical types of statements that we meet in mathematics, discrete mathematics, and computer science. In particular, mathematical induction is among those templates one that is particularly powerful because it gives you a totally different angle to prove things compared to the more direct ways, say. And then we'll see how proofs connect to algorithms. There's two things that people want to prove about computer programs. Usually they want to prove that they terminate, that they eventually finish for a computation where this makes sense. And they want to prove that it computes the correct result. We won't obsess much with either in this class. We'll often discuss more informally how we can argue that a certain algorithm computes what we want it to compute and what we think it computes. But I want to highlight how you could, at least in principle, do this. It's just a lot of effort and a lot of work, and most of the time we will stay on a higher level. but I think it's insightful to learn on a small example how this would look like if you zoom in into all the nitty-gritty details. So that's what I want you to take from this. And that also reflects the structure. We'll start from the basic proof templates, work our way up to induction, and then have a look at these applications. So if we start from nothing, you can ask what a proof is to start with. It's actually a very interesting question. I might post some further pointers on CoMP526 if you're interested. It's a philosophical question. If you come from ancient Greece, they already asked this question, and you might have seen geometry proofs in school. That's usually the first type of very formal way of specifying proofs. And then I took till the mid of the 20th century to really nail it down, what a proof is. I think now we have a definitive understanding, but who knows? But I think it's very solid. The idea of a proof is to have, sorry for the pun, a bulletproof statement, a bulletproof argument that something is correct or something is true. And so while we will in this class mostly convince other humans that a certain statement is true, which could be the topic of politics as well, we use this just as an excuse to not always go to all the details, just because we won't get much further in this. It just takes very much a long time to write all the details down. But we want to write proofs for humans so that a qualified human can fill in all the missing steps. That's the idea. And the missing steps would be a sequence of statements that are derived from axioms. These are things that we accept as true, and well, we'll maybe see some examples, and inference rules, which are very syntactic rules, just operating on symbols, how to go from one correct statement to another correct statement. And if you can puzzle something together, starting from axioms and only using the inference rules that are allowed, that is a formal proof. We won't usually go down to this level. We'll use a little bit of notation for this. And it's, I'll keep it a bit informal here, but we use statements, and these uppercase letters represent a certain statement. I used examples here that are somewhat from the real world, but you'll see that it often has limits. So most of the time when you want to prove something, it's more a statement about numbers or maybe about programs and algorithms. So we can have different statements. Say it rains, which is false at the moment, and the street is wet, which interestingly might be true depending on where you look. If we have a statement, we can negate it. So we can put this negation sign in front of it, and we read this as not A. If you spell it out in English, you would say it does not rain. So natural language has slightly different constructs, but we have the same conceptual ideas. You can take a statement, you can negate it by putting not in there in some way or another. You can also take two statements and put an and between them. That means you require both of them to be true. You can do something similar. You can put an or between them. That means one of them can be true or both. So that's an important thing to point out here. If we say A or B, it's fine if A and B are true. There is also the exclusive or. Maybe in English you would say either A or B. And there's no very standard notation for this. But let's say we just write X or, which stands for exclusive or. So it's either A or B, but not both. That's just for context. I don't recall that this pops up anywhere in our module. More interesting are the things, the last 2 points. An implication is if A then B in natural language. But it's probably better to keep this in mind. We'll come back to this in a second. But implication means if A holds, then B has to hold. An equivalence between two statements, sometimes also called a characterization, in English we say A holds if and only if B holds. So you can also write this as an implication in both directions. A implies B and B implies A, then they are equivalent. Okay. Just quick hands. Has anyone not seen this at all? These type of operators and rules, etc. Everyone has seen it? Good, then the next question is easy for you guys. I'll start it. Okay. So you should be able to vote. This fun problem again. I hope you didn't pay attention. It was revealing the correct answer already. We have a few more people than 38, 40. Anyone still busy voting? Yeah, sorry for spoiling this one, as you've already seen if you were paying attention. Yes is correct. The more interesting part may be why. So the trick about this statement is, okay, unless you're believing in this weird conspiracy theory that you might have heard of, the flat earthers, I think most people believe the Earth is not flat. So that makes the statement kind of empty. If the Earth were flat, then maybe, yeah, maybe ships fall off the rim and all sorts of weird things happen. But we don't really believe this is of any relevance because already the premise is false. But the thing is, these statements of this form, implication A implies B. So what we have is two statements. A, the Earth is flat. And B, ships fall off the rim. And the statement we're concerned with is an implication. A implies B. That's what we claim. And if you remember from the last slide, this was the same as saying B or not A. So these two are equivalent. Let me write this with these the equality sign with three things. It's not supposed to mean they're equal. It means they're equivalent. We could also say the arrow that implies each other, but you have to be a bit careful what is part of the statement and what is part of a statement about statements. If you take a look at this, then we know A is false. So this OR is already true because A is false. So that's all we need. And it doesn't matter that B is probably also false, right? So the entire statement is true, which means you can make any claims after an if, then after the then if the if part is false, okay? That's just how it is defined. An implication is defined to mean exactly this. And that's important for you because if you want to prove something, sometimes you have to use the fact that if A is already false, what you're trying to prove is trivially true, meaning you don't have to do anything else. So you have to know that an implication has this meaning. You might not agree that this makes sense, but the rest of mathematics has decided this is the way to go, so you're kind of out of luck, I guess. So that's the first thing to pay attention to. I think all the other notions, if you look at all the other operators and their English language equivalent, they are doing what you intuitively expect them to do. Implication is the only kind of slightly tricky one. All right. With that setup, we can now look at some proof templates where I called them strategies before. So these are templates how you can structure a formal proof. And the idea of presenting them is to help you get started. The tough part is then filling the template. But without the template, it's even tougher. So they still help. There's different templates depending on the type of statement you try to prove. If the statement you try to prove is an implication, like we just had the example, there's these 4 different ways how you could go about with this. You could do a direct proof, which means you assume that A is true, and then you try to show with logical reasoning that B is also true. That would have failed in the previous example, because if we start with assuming the Earth is flat, you become a weird person, I guess. Another option is an indirect proof. So you start by assuming that the B part, the conclusion, is false. Like in our case, ships don't fall off the rim. Okay, maybe we can live with that because there is no rim. And you can then derive that also A has to be false from that. So if ships never fall off the rim, the Earth can't be flat. Maybe. It's a little shaky argument. But because not A was easy to prove, if you're already convinced of that, this would be the way to go in this example. We assume not B. If you believe whether ships can fall off a rim or not doesn't really make a difference, you assume this here. This is your starting point of the proof. And assuming this, you want to show that A is not true, which we already believe, so that's the end of the proof for us. Okay? Something similar, but slightly different in how you structure it. We'll see more examples of this later in the class. That's often a convenient thing to do. Try to derive a contradiction by assuming A is true, but what A would imply if the statement was true is not true. It's sometimes easier if you just go back to the symbols. So if A implies B, you could start with A and not B and try to bring this into a conclusion, into a contradiction. So that's called proof by contradiction then. And something that's slightly orthogonal to the other cases, you can do this in general in a sense. You can distinguish different cases, and it looks like in the formulas, it doesn't look like it helps much, but often this additional assumption makes different arguments easier go through. So you can say, I'm not only assuming A, but I'm assuming A and C, some additional assumption. And those two together imply B. That's good, at least part way there. If you can also show that A and the negation of C also imply B, then you're actually done. You have distinguished 2 cases, and maybe the proof was different in the 2 cases, but taking the 2 proofs together proves the entire statement that A implies B. Many puzzle faces. This is all a bit dry, right? Let's practice this a bit. You read the question. I'll make sure that I don't reveal the answer this time before we get started. I opened the question already, but maybe before we dive into this, let me do the actual proof. And your task is to find out what proof template I was using there. That's the options. So we have this innocent statement. If n squared is an even number, then n is also even. If you think about it, maybe try a few examples. Seems true, right? How would you prove this? Well, one way to go about proving it is say, let's assume n is odd. So if n is odd, that means I can write n as in the form 2 times k plus 1 for some, well, let's be generous, some integer k. We don't care about negative numbers for now. Okay? What does this mean? Well, that means if I take n squared, I can write n squared also in this form. And if I pull this out, then you may notice that there's, again, sorry, another 2. So you can write this again in this form. And this is another integer. Whenever I start with an integer, I can take a square, multiply by 2, and add another integer. I will never get a fractional number. So this means that n squared can also be written in the form 2 times an integer plus 1, which means it's an odd number. Okay, great. That's the statement we were trying to prove. Okay, sorry about the rim. End of proof. Something like this, as short and terse as this, might be something you do in some number theory, discrete math 101 class. You may have seen this proof before, or it may be obvious to you how this works, or it may not be so obvious. But I'm just asking you, what proof template did we follow? And so if you haven't voted on Slido yet, now is the time to do that. So we had 63 people on the last question. 20 more to go. If you don't have an idea, maybe this time it's fine to just guess. So again, remember, I want to give you participation marks for answering all those questions, but it doesn't matter if you're right or wrong. It's more just to make sure you're active. Can we get 9 more people? A few more people? I won't show the answer before I close it. 3, 2, 1. All right, now we want to see. I stopped it, but what I actually wanted to do is lock it. Sorry. Can we get all the answers? Not really. All right, most of you got this right. It was an indirect proof, but maybe it's insightful to still quickly highlight what A and B, etc., was in this case. So shall we briefly highlight what A and B was? If anyone feels comfortable shouting it out. The statement to prove was A implies B. Where can I find A? Exactly. Where's B? Nice. Yeah, that's it. So that's A, that's B. And so this was a bit sneaky. I didn't say n is not even. I said n is odd, which is the same thing, just to confuse you guys a bit. But that's the same as not B. And then we followed. This implies, again, same trick, not A. Odd is the same as not even. Do we need to discuss a bit more? Confused? Oh, sorry, yeah. We can try to get both on one screen. Oh, not on your screen. so you didn't see what I was writing. That's the confusion. So that was the proof, and here's my nice way of marking A and B and not A and not B, etc. Okay? So the confusion was more that I wasn't showing my screen and not that you're not following the proof. You should tell me if I'm doing nonsense. All right. That was all about implications. There's many other types of statements we sometimes want to prove. One example is equivalences. So these characterizations. But these can conveniently be reduced to the case we've just covered, because an equivalence is just two implications taken together. So indeed, the typical proof template for proving an equivalence is showing both implications separately. Sometimes a direct proof showing the equivalence works as well, but it's usually easier, just a little more to write, to do the two implications. So it's actually nothing new. Sometimes we want to make statements about sets. For example, that one set is a subset of another. So here R is a subset of S, in case you haven't seen this symbol before, but I hope you have. Again, we can reduce this to something we already know. It's just an implication saying that whenever I take an element in X, this implies that this same element is also in the other set S. Okay? So in a sense, it's just a hidden implication. And similarly, if you have two sets and you want to show that the two sets are equal, that's a hidden equivalence, which you could prove like this. If X is in R, that's equivalent to X is in S, and then you can prove both implications. Another way to arrive at the same thing, set equivalence is the same as saying one set is contained in the other and vice versa, and then you also get both implications. Okay, it looks like everything's really an implication and there's nothing new under the sun. I'm running fast through these, but stop me if something's unclear. I think these are not your problem. In the next subsection, we want to look at a slightly different type of statement where we do need some different templates for proving them. And most famously, it's mathematical induction. There's a few smaller ones hidden in this section as well. The new type of statements I'm referring to are quantified statements. And that's where these weird symbols come into the game. These are called quantifiers. And for those to make sense, we need statements that have a parameter, something like this. So if I write a of x, I mean this is a statement where there's something variable, this x that occurs in it. And the statement could be true or false. It really depends on x. Like if I put in x equals 4, then the statement is true. But if I put in 3, it's false. So it depends, right? I can take such a parameterized statement and stick an existential quantifier in front of it. Then I'm turning it into a statement that says there is some value for x that makes a of x true. So in English, there exists some x so that a of x holds true. And I can do this for all symbol, another quantifier that turns the statement into for all x, a of x is true. And well, often we want to restrict x to a certain range, a certain set. This one, you want to repeat? You want me to repeat what I said on this slide? Yeah. We can have statements with parameters. So it's a statement that is true or false depending on what you plug in. There's something x in this case. And if x is 4, the statement's true. If x is 3, the statement's false. So it doesn't make sense to ask if a of x is true or false. It only makes sense after you substitute x with something concrete. These types of parameterized statements can be decorated by putting one of these symbols in front. And then it makes sense to ask for the entire statement whether it's true or false. And the meaning of these two is there exists at least some value for x that makes the statement true, or for all possible values of x, the statement is true. Okay? Yeah, it's important concepts. If you haven't seen these symbols in some math classes, these are really occurring a lot, not just in our module. It's useful to know those. Again, we can restrict our attention to one of the two. We can say for all can be written as there is no x so that a does not hold. So that's the same as saying for all x, a holds. But still, for proving statements, this doesn't usually help you very much. You need different strategies for the two types of statements. I want to mention this concrete example of a statement involving several quantifiers because it's a famous one. It's a very important one, an interesting one. I hope many of you have seen it before. But it also illustrates some corner cases that makes these quantifiers a little tricky. So what this statement, what this formula here formally says is there's a certain function that depends on a parameter x. And we want to say as x approaches a certain value xi, the function approaches a value x. So the limit of the function as x goes to xi is a. You could have xi could be plus or minus infinity, and same for a. So there's some extensions of this, but it also works with concrete numbers. Limits are everywhere in math. And people argued for a long time how to formally deal with this. And the definitive answer is the epsilon delta criterion. So you say that this statement is the same as claiming for every epsilon of an error that you allow between the function, the actual function value, and a. So you're at the end claiming that the function must be closer to a than epsilon. For every such error bound you give, there is a delta, so that if x is closer to xi than delta, the function value is closer to a than epsilon. Okay? So epsilon and delta are just ranges on the x and y scale if you plot the graph of this function. But it's important that the order of the quantifiers is as given. For every epsilon, there is a delta, and this delta can depend on epsilon. It usually does. Okay? You've all had some analysis class, real analysis at some point, I guess. It just might be buried deep in your memory. All right. We're not really building on this definition so much. It's just an example how quantifiers can be tricky. Okay, so don't get too obsessed with the details if they're not clear. For this unit, we're talking just about the proof templates. So we don't want to get too involved into any of these problems. A simple template is for the existential quantification. If you have a statement, there is an x, so that a of x holds, well, you just find an example and be merry. So you try to find one value for, let's pick our example from above. If this is your statement, I'll say you pick x equals 4, and then the statement's true, job done. Okay, so existential is usually easier. The tricky one are the for all statements. And before we come to this, let's see if you've seen induction before. Again, computer science undergrads would have seen this up and down, I guess, but maybe not everyone. As I said before, I think around half to 2/3 of you are not CS undergrads. That was the numbers from last year. I'll check the details from the survey for Monday. All right, just a few people missing, but I guess it's fair to say that half of you have seen it and are still comfortable doing it. Most of you have seen it, but maybe not everyone's completely ready and set to go if I would give you something to prove by induction, which I think we'll do next week in the tutorials. So you'll be all on the same page after that. All right, so let's do a recap what this mystical mathematical induction is. As I said, it's all about proving the for all quantified statements. The existential quantification is not so tricky. So if we have a statement like this, one way to go in general is you assume x is some arbitrary value that you know nothing about, and you try to still prove just from that a of x holds. If you can do that, then you've proven for all x a of x. That has nothing to do with induction. That works in principle, but also it's a very weak template because it gives you hardly anything. It's just a way of writing down a proof. If you additionally know more about x, that x is from, say, just the natural numbers, an integer, and starting from some range, say from 0, then you can use induction. And for that, you prove two things. First, you show that for the smallest value in your range, 0, the statement is true. That's called the induction basis. And then you show this slightly more complicated statement using one of the techniques that we've seen before. So for this for all, you would probably have to use this first bullet. And then you have an implication which we've talked about at length. Now, it might seem on this formal way of describing things, it might seem like we go from a fairly clean statement for all x, a of x, to something much more complicated. Why on earth would that help us? Why should we torture ourselves like this? But the trick is that the more complicated statement gives you more to start your proof with, because you're proving an implication that assumes the same statement you're trying to prove just for a smaller parameter. And that's often very powerful to make the next step. It's almost magic sometimes. You can just guess a solution and prove it correct by induction. That way you get a formally proven result without having any intuition into why it holds. So we'll have an example in the tutorials. Another one, the standard one that you often see is the little Gauss formula, the sum of the first n integers. Right, you know about this one. So if you sum from 1 up to n I. So again, this summation formula, the summation symbol is probably known to you, but just in case. So this is a shorthand for writing 1 plus 2 plus 3 and so on up till n. And it's like an integral. You say there's a starting point, there's an ending point, and then you sum up a certain term. And there's a closed formula for this thing, which is n times n plus 1 divided by 2. And legend has it that young Gauss discovered this formula in his primary school days when his teacher allegedly wanted to keep them busy for some time, and he just finished it after a few minutes. I don't know if that's true, but it's a lovely story, and that's maybe good enough by itself. Now, for this formula, you can find very nice intuitive explanations why this is true. For example, write the sum out once and then write it again below, but in reverse, and then you notice that the terms match up and have the same sum all the time. But there's also an easy way to prove it by induction. Looking at the time, maybe I don't do that in detail here. I think this is repetition for almost all of you. And you'll practice induction in the tutorials again. So you can ask Ben if you feel like you need more preparation on this. I want to highlight two things. this form of induction is sometimes called the weak induction, if you want, and it's contrasted to the strong induction, where instead of just assuming a of n for the last parameter, you can assume it for all the previous values together. And the template works in pretty much the same way. So the intuition behind induction in both cases is you start with A0, which you have proven true in the induction basis. And then from that, you get an implication that A1 is true. And so now you know two things. And from that, you can derive that A2 is true, again, by this implication that you've proven here. And so you can build up this ladder of statements added to infinity. And then the principle of induction says this is enough to prove the statement with for all. There are more fancy versions of induction. Just to mention this, that it's not restricted to natural numbers. And discrete math, computer science often uses these kinds of statements. I don't think we'll need it in this class, so I just wanted to mention it, put it on the slide so that you can Google the term if you want. You can use induction for any other recursively defined object where you have something like a size that is never below a value and only goes up in a somewhat structured way. The formal thing is you need a well-ordered set, but okay. We don't need that detail. I think that's a good point to have a 5-minute break. If you need to go to the restroom, you can do that. Or you just slack off for a few minutes. And then we'll continue with the last chapter for that unit. All right. So say we continue. Yeah.
Yeah, I noticed that it was about the second class test, and I noticed that there's not a constraint that n is an integer. So I think
Sorry,
I
can
think,
you which slide is this about? Is it about
just on the studio, just the
this one?
internet. Yeah. No, no, no. And before this, before yeah, this one.
Uh-huh.
Yeah, and I think there's not a constraint. N is the strictly integer, and so I think
Okay,
there's
yeah, you're right.
I think there should be the third condition that n is neither an even or an odd.
Okay, so there's two answers to this if you want. In a way, if you write a statement like this, you usually want to say what n is. And I should have probably written n is an integer. And then we start from there, then the rest is the same. N is conventionally often meant to be an integer, but of course you can't rely on this, right? The other option is you allow non-integers, but then the question is, what does even and odd even mean?
Yeah,
It's not really defined for reals.
Even in the field of integers, but
Yeah.
and there's maybe any float or maybe a double float or any other.
Yeah.
Yeah. So I think it should be strict, more strict. That's about the so
Let's see if the proof still works, though.
I just
So
chose
if
the last Because I think
Sure.
yeah for this n is odd, and beside this there's the third.
Yeah, that's the third option that it's neither.
N
You're right.
is
Yeah.
odd.
Yeah. And so if n is not an integer and you square it, it
Yeah,
might
and-
become an integer, and so it's not so clear. Yeah.
And
If,
this, I think
yeah.
this statement is not correct.
Yeah, you're right.
Maybe,
It's
yeah.
only true on integers. Yeah.
For instance, n squared is 2.
Yeah.
So n is
Yeah. Let's put this here. You're totally right.
yeah.
That's enough for us. Yeah. Yeah. Good point.
No, why this can be changed?
Pardon?
Why this can be changed to this?
What do you mean by change to? The whole thing is just a definition, right? It's something you want, something you require for this to be true. If you want to say that a function has this limit, then you have to show this. All right, guys. According to my watch, it's 52. Apologies for everyone on the live stream. That scream was probably terribly loud. All right, hope you got a little bit of a breathe and fresh energy for the last chapter. In the last section, I want to talk about correctness proofs, so bringing all the talk about proofs and proof templates back to algorithms and computer science. And I want to go through one example in more detail, so I might sit down for that part. The idea here is give you a glimpse of formal verification. And verification is a fancy word of, in this context, saying proof that a program is correct. And correct usually means two things. It terminates and it computes the correct answer, both of which usually prove in isolation. But we take them together as the statement the program is correct. Although formal verification is not our focus in this module, some of the techniques are useful for us because we do want to derive efficient algorithms, and sometimes something is obviously fast but not completely clear why it does something useful or even correctly computes what we specifically want. And we will sometimes borrow some of the ideas from this to convince you. Even though maybe a very formal argument we will usually just sketch. So we have two things that together mean correct. And as I said, we prove them separately. So guess what? There's a different proof template for each of them. The first part is about proving that some program you wrote eventually stops. Now you may know the halting problem and the undecidability of that, and so we can't always, we can't write a program to do that for us, that given a program tells us whether a program halts, but that doesn't mean that you can't do it with a specific program, because you're not a Turing machine. And for the examples that I have in mind, it's not like someone gives you an arbitrarily complicated program, but you design one. So for those ones, we hopefully are able to prove that they terminate. And here's a proof template how you could do this. I formulated it here as a potential function, which sounds really fancy in all the Greek letters. I think the concept, though, is actually quite intuitive. What we'll use at the end of the day is that if you start with a natural number and you make it decrease by at least 1, because it's an integer in each step, if you make it strictly smaller in each step, after a finite amount of time, you will reach 0. So if you can somehow prove that the parameters of your program, if it's formulated for a recursive program here, so you have some procedure proc that has parameters, and it calls itself recursively, maybe many times. But if you can show that somehow these parameters get smaller in a certain sense, and you stop if you reach 0, then you're done. Then you have proven that it always terminates. I might stress that this is not about proving something, how fast it terminates. It's just about whether or not at all it ever stops. Okay, so we define this potential function that can be just any function you can come up with. It takes the parameters of the program and it computes some natural number. And here it's important that it's a natural number, not just an integer. So I'll write n0 for natural numbers starting at 0. So this potential is always non-negative or weakly positive. And the thing that the proof template tells you to do is prove whenever you have a recursive call. So you would have to think about it that there's some code, I don't know, Python code, where there's something done, and then there's another call to the same procedure again. With some other parameters that you compute from X, probably. And then you keep going. And there's also some place where you return. So you look at your Python code and you see if there is a recursive call. If that's the case, you try to show that in any such recursive call as it's shown here, the potential of the parameters of the recursive call are strictly smaller than the parameters of the call you started with. What I didn't put on the slides, but what's hidden here is essentially a big for all x1, x2 up to xm. It's an all quantified statement again. You want to show for all choices of the input parameters, every recursive call decreases the potential. Okay. And that's as far as the template goes. Then the second part is easy. If you've shown this, then whenever you call the function, there's some potential that you start with, and it only ever gets smaller, and it has to go down by at least 1 in each step, so it will reach 0 after a finite amount of time. And actually, you could say the potential even bounds the running time, but we don't focus on that in this unit. Okay, I formulated it here for a recursive function instead of a while loop, but as you may know, you can usually write one in terms of the other, or vice versa. You can translate from one to the other, and you can adapt the template for loops in pretty much the same way. You have some point at the beginning of the loop where you say, now I measure my potential in terms of some variables, and then whenever the loop runs one more time, that potential has to decrease. So same conceptual idea, just slightly different formulated. You will do a detailed example in the tutorials, so this is all I want to say about termination proofs for this unit. So what's left for us is the second part, which is, I think, a little more subtle. That's why I want to go through that in detail. That's the correctness part that you compute. If you ever terminate, you compute the correct answer. And the template for this are so-called loop invariants. Okay, I should have put this on slider. Anyone seen Hoare calculus? 1, 2, few more. Hoare calculus for proving statements like this, and loop invariants, etc. So Tony Hoare invented this way of proof templates for correctness. So it's named after him. The same person who invented quicksort, if you're interested in these historical facts. Okay, the template works as follows. You have a code fragment like this on the left here. There's a while loop. And again, now we're not concerned about termination. We already assume that this terminates. The question is, what does it compute for us? And there's 4 interesting points. It's directly before the loop, just at the beginning, inside the loop body, but at the top. The same thing at the end of the loop body, and then again after the loop, straight after you terminate from the loop, there's another interesting point in time or in code. And so the template tells you you should find a loop invariant. So I is some statement about the current value of variables. It can be some complicated construction again. The template doesn't tell you how to find the loop invariant. This is up to your creativity, imagination, ingenuity. This is usually what's challenging. But the template then tells you if you have found the correct loop invariant, you can prove the following for 3 things, and then you have proven a certain statement. The first thing you want to prove is that the invariant holds at A before the loop starts. Then you want to prove the invariant plus the condition that tells you whether to continue the loop. Those 2 things together imply that at the end of the loop body, the invariant still holds, or holds again. And the third thing you should prove is if you take the loop invariant and you add the negation of the while condition, so which another way of saying the loop invariant together with the fact that you stopped the while loop, that together implies the desired post condition. Okay, we'll have to see what this means. But the statement we're trying to prove here is if before the loop something is true, so we make some conditions. If you want to reach this piece of code, you should make sure, please, dear user, make sure that certain conditions are met. And then I promise you, if you keep your promise, I promise you that after the loop, something else holds. And we're trying to prove this implication. If the precondition is fulfilled before the loop, then this condition is true after the loop. What these 2 conditions are is, again, up to you. It depends what you want to show. But this will be clear in the example, I think. So that's the template. Magically find a loop invariant. I don't tell you how, just do it. And then check that these 3 things are proven. Okay? That's what the template says. And so let's look at this example together, where we apply this on a concrete example. It's a simple procedure. You can maybe read over it. You've probably written something like this in some programming language. So it's given an array A and the length of this array, and you're trying to find the biggest element in that array. It's really fancy and complicated. And the function does the obvious thing. It loops through the array, keeps the current maximum, and at the end spits that out. It's probably what you would have done if I would have told you to program this. I know that many languages have something built in to do this even, but let's pretend you don't have that. So the point is not that this is an interesting algorithm. The point is that we want to prove such a correctness for this piece of code. And so here you see it's usually easy to come up with these pre and post conditions if you know what you want from this function. Sometimes the edge cases are a bit tricky. So the precondition means you can only call this function for certain values. And here, what we want is that the array is not empty. We insist that there's at least one element in it. And indeed, if you think about it, computing the maximum of an empty array is a bit pointless, and it's not clear what you should return. So this is kind of reasonable, but we don't make any other assumption other than that array elements can be compared. So there's a point here where we use a comparison operator to compare two elements from the array. And we assume that this is somehow well defined. So maybe it's numbers. Maybe I should have just said here integers or so to make life a bit more concrete. But it would work for anything where you can compare. And so the only real restriction is I want an array and at least one element in it. That's a weak precondition, doesn't require much. The post condition is a bit more interesting. It says the output of the function, whatever you return, is the biggest element in the array. So here I just said the maximum element in the array. If there's several maxima, we don't really care. We could strengthen the statement because that procedure will probably return the first of these occurrences, but maybe it's numbers and they're all the same, so it doesn't matter. Okay. So I don't know if it makes sense to write this down. I don't think I have the precondition on the slides. So let's say given A is an array of numbers. And we want at least one. And then the post condition for the entire function is that the output is the maximum element. So that's what's written here. Should use this notation. So let's see how we apply the template. Let's first pick the easy parts. The loop condition, what I called cont before, that's just this part. What is here in the loop. So we just copy that out. We can work our way back up. So here we return current max. So if we translate just the post condition I showed here, you can hardly see this move, right? That's not much better. I could use the mouse. Well, next time I bring a mouse. There's a tiny little dot that moves. Can you just barely see this? If we take this post condition and we replace output with current max, then we get what's written here. So that's what we want to hold in line 30. Okay. And I also already solved the tough part of finding a loop invariant. That's this one here. Now, if you look at this loop, it iterates through the array. So you have seen a prefix of the array, and current max is the current maximum of this prefix. So this first part is maybe quite intuitive. If with the current value of I, you want that current max is the maximum in this range up to I. It turns out it's excluding I itself. What's maybe a little more mysterious is why you have the second part. You also require in the loop condition that I is never bigger than n. That seems a little less clear where this comes from. And the answer is you try with the first guess that sounds intuitive, and you see it doesn't go through. And then you keep adding things to the loop invariant. That's how you get to this. That's what I already did. So with this said, the template tells us to prove these three things. So let's see how we do that. For the first part, we have to prove that the invariant holds at position A. So we look at the loop invariant. At this point, we have just set I to 1, and we have just set current max to the first element in the array. So yeah, one thing I should have mentioned, arrays always start with 0 for this module, wherever it makes a difference. I think that's the convention in Java and in Python and in most languages that makes sense. R is different, in case you know about that one. But most languages start with 0, so that's the convention I also picked. So this is what we've just done in the line before. So if we just plug that into the statement of the loop invariant, we see that current max should be the maximum over all k between, well, what is this? K between 0 and 0. Okay, I can do that. And because that's a single element, it is just A0, A of 0. And so that's correct because we just set current max to this value. Okay, so that's the first part. Let's maybe mark this in red. And we have a second part that we can mark in blue. So that means the red part is proven. Clear? How about the second part? Well, for that, we need our precondition. That n is at least 1. And so we set I to 1. So I is also at most n. And that proves the blue part. Okay? So that's the kind of baby steps if you want to go all the way to the details, how you can prove this. Now let's look at the second condition. This is the more interesting one. What happens in the loop body? So we'll need a bit more space for that, but I'll probably have to scroll back and forth to the code. So we assume that the loop invariant holds at the beginning of the loop body plus also the condition, the loop condition, which again was I is strictly less than n, if you remember from here. And now we want to show that the loop invariant is reestablished at point C. Now the trouble is that various things change in the loop body. In particular, we might reassign current max, and we definitely increment I. So you somehow have to deal with that. And here's a good case where we can distinguish what happens by looking at what the if does. And the first case is that the maximum in the prefix we're looking at the moment, so from 0 up to I, dot, is at this last position. Okay? In that case, we enter the if statement because then, so that's the first case, and we'll have a second case that we have to deal with later, and that's that the maximum is not this value. That's case 2. For case 1, we intuitively know we will enter this if statement. But how can we prove this from what we know formally, namely the loop invariant and the condition? The loop invariant implies that current max is the maximum up to I minus 1, okay? So it's important to stress that here we want up to I, and here it's only up to I minus 1. And we know in this case that the maximum of this range is the last element. And I want that it's the unique maximum. I think it's more convenient to write the case distinction like this. This new element is bigger. Well, it's not. Is the AK missing? So we still have a valid case distinction, but I changed the case distinction, as what often happens if you do proofs. I can get rid of that red part though. So we know current max from the loop invariant is the maximum in this range. So this condition, this case immediately tells us that then current max, oops, not what I wanted, current max is strictly less than a of I. That's just using this equality in and the case and the condition of the case. And that's the condition asked in the if statement. Okay, so we enter line 9 and change current max. So after this line, current max has a new value, and it's a of I. And then after that, we always increment I no matter what. And so now we're at the point where we want to go. Now we have to show that the loop invariant holds again. So we want to derive from this that I holds again. That's what we want. And if we take the case assumption, that means I don't know. Take this statement. That implies that if I take the one bigger prefix, that this is a of I. Because the next value, a of I, is bigger than all the previous ones. Okay? Now the annoying part is that I keeps changing the values, so we have to pay attention which I we mean, the one before we changed it, the one after we changed it. So we might want to give this a prime just to make sure that we're talking about the new one, the new value of this variable. And so if you look at this, if you just insert what I prime is here, then this is exactly the same term. So these two are the same. And we've just set current max to AI, so these are also the same. So in this case, we've reestablished the first part of the loop invariant, the red part. And for the second part, we need the loop condition, which again, remember that loop condition was I is strictly less than n. I was strictly less than n, so I prime is still at most n, because we just added 1. And so that's this second part that we wanted to prove. Okay? So in case 1, we've reestablished the loop invariant at the bottom of the loop body. We still have this second case to deal with. Should have left a bit more space, but just move it around a bit. The second case is actually easier because it's the one where we don't need the if statement. If you look at this condition, it means that this new element is not a new maximum. Strictly means that well, that's true, but that's not helpful. We want to use the loop invariant. So by I, we know that this is the current value of current max. Let's write this differently. So current max is greater or equal than A of I, which means in the code we don't enter this if statement. So our new value for current max is the same as the old value. We don't change it. That's the first part, but we do increment I. So we have this I prime is set to I plus 1. And now we just look at the loop invariant again and see what has changed. So we take this part. If we go up to I prime minus 1, then that just includes the value I, but that one is smaller than the previous maximum. And that was current maximum. And so it's still current max prime. Okay, we need more space. because current max prime is the same as current max, and current max by the loop invariant was this maximum up to I minus 1. And if you check, this is the red part of the loop invariant over here. And for the second part, the same argument is true. The blue part, nothing has changed. N is still, we still have the loop condition that I is strictly less than N, and we increment it by 1. Okay, so that concludes the proof of the second part. We've done this one, we've done this one. What remains is that to show that at the end, it has actually helped us. But that's much easier. So we take our loop invariant, and we add together the negation of this condition. So last time, current max is the maximum for k between 0 and I minus 1. And we have I at most n, and the negated loop condition. So not I is strictly less than n means I greater equal n. Okay? And now these two things together, if I is at most n and at least n, it can only be n. And that means we can insert the value n for I in the first part. So if you insert this one here, then you get that current maximum is the maximum of the array from 0 up to n minus 1. That's the entire array. Okay? And that's what we wanted. So that was the somewhat longish proof that if you start with an array and n at least 1, you end with actually the maximum. This was a tiny example, and it took some back and forth with the cases and almost half an hour to spell out. Maybe if I prepare it without making mistakes, maybe I can squeeze it into 20 minutes with the same explanation, but it's still quite tedious, right? So we will usually not go all the way down to these steps, but any proof you write should be possible to be expanded like this. Otherwise, it's not a real proof. You will have some gaps in there. Questions?
Based on the fact that it is an ordered set of numbers.
Yeah, the question was, I'm assuming that the array is ordered. Yeah, in a sense, the code doesn't make sense at this point. We compare two elements from the array, and if that comparison doesn't have a meaning, then the code doesn't have a meaning. So that's why I smuggled in the precondition that we have a set of an array of numbers where the comparison is clear, but it's a little more general. Whenever you cannot define a comparison, it's fine. But we need that assumption, yeah. All right, good. That's all for today. That's all for the proof techniques. On Monday, we'll start slowly with getting to models and machines, more on the algorithmic side. And we'll start next week with data structures as well. Have a nice weekend. See you on Monday. Yeah.